Hi everyone, welcome to the walkthrough for problem 1 of Spring 21, Midterm 2. This problem goes over graph traversals. So we're going to start by asking, if we perform VFS traversal starting from vertex 7, what will be the final vertex visited? And so we recall that BFS is also known as level order search, which means it's going based off the edge distance from the start. And so here, if we start at 7, we see that we're going to visit all the things that are 1 edge away from 7 first. Then we'll visit the things that are 2 edges away, and so on and so forth. And so I think a lot of people find BFS more natural if you think about it in like a tree-like pattern, right? Because then you can see the levels going straight down. And so one way to approach this problem would maybe be to try redrawing this little graph as something that looks more like a traditional tree. And so this is definitely an approach you can take, but you don't have to. But I will just demonstrate. And so we see that, for example, 7 has the children 1, 5, 3, 1 and 5 are connected, 5 has a child 4, 4 has children 8 and 2, and lastly 2 has a child 6. And so based off this visual, to me now, it's pretty clear that 6 is on the lowest level because each of these are 1 level going across like this. And we see 6 is on the lowest level, which means it will be visited last by breadth first search, because breadth first search visits, I guess, the breadth or everything on 1 layer before it goes deeper. And so the things at the deepest layers will be discovered last. Another way you could have done this without redrawing the whole thing would maybe be to just go through and count how many edges away every node is. And so we can see vertex 3 is 1 edge away. So we'll just note that here. Vertex 1 is 1 edge away. Vertex 5 is 1 edge away. You're going to note that we don't say 5 is 2 edges away because it is possible for 7 and 5 to directly traverse like 1 edge to get there. And breadth first search will definitely traverse this edge. So these are all 1 away. We see that 4 is 2 edges away. 8 is 3 edges away, as is 2. And we can see that by taking these edges 1, 2, 3, or 1, 2, 3. And finally, we see 6 is 4 edges away. And so it's definitely the farthest, which means it will be visited last in our breadth first search. And that is part A. The next question says, which start vertex or vertices will result in a DFS preorder of 8, 4, 2, 6, 5, 1, 7, 3? Assume ties are broken numerically, and if no start vertex would yield this order, then select impossible. And so we're going to recall that DFS preorder means we visit the parent, or we mark the parent, and then we go look at its child, and then the next child, and then the next child. And we go deeper before we go wider, which means we're going to keep sort of recursively looking at the next child and then go back up and say, okay, where was I? And do that to the next child. Oh, also, maybe for A, that means the answer is 6. Kind of skipped over that part, actually bubbling it in. Okay, so for B, we're looking at this DFS preorder, and we're going to say we want to visit 8 first. And so just looking at this, we know DFS preorder will mark the parent before we mark the children, which means if 8 is the first thing we mark, it must be the first node or vertex we see, because we'll mark 8 immediately. And so we can imagine, okay, let's say we were doing DFS starting from 8. Is it possible to get this order? Well, if we start at 8, then we see we're going to visit 4, at which point we will visit 2, then 6. And from 4, you're going to note we chose to visit 2 because 2 is numerically lower than 5, and we said we were breaking ties numerically. Once we visit 2, we continue going down its child path rather than coming up and doing this edge, because in DFS, we are always going to be looking at the children first, like digging recursively and recursively deeper, not going wider in that sense. And so we go to 2 and we visit 6, and now 6 has no more children, so we can come back up. But so far, so good. We've got this order 8, 4, 2, 6. Then we see we're going to come back and say, okay, where was I again? At this node 4. And now we'll visit 5, which makes sense. Then 5 has 2 children, 1 and 7. And so we visit 1 first, because again, we're breaking ties numerically. So we go to visit 1, and then we dig deeper on 1. And we say, okay, 1, who's your child? And it only has 7. And so we go, okay, that's fine. And 7, who's your child? Well, that's 3. And you're going to note again that technically on this undirected graph, it might be hard for you to think about who is whose child because it's not a clear relationship. It might be more accurate to actually say neighbor. But the idea is just that we want to go to some neighbor that has not been visited next, and we'll consider those the children, so to speak. And so, for example, that's why we said 7's child was just 3. We're not really going to go back and visit 5 because we've already marked it. And so we visit all of the neighbors, and then we come back up to 5, and we've seen both of its neighbors or children, however you want to call them. And we realized we got that order we wanted, right? We saw 5, 1, 7, 3 at the end. And so I've concluded that if we start at the node 8, then we can get this order. And I just want to emphasize the whole way that I sort of determined it was 8 to begin with was because in DFS preorder, we visit the parent first. That's the first thing we mark. And so we should be starting there. Now, we want to know what start vertex or vertices will result in a DFS post order of 8, 4, 2, 6, 5, 1, 7, 3. And again, we're going to assume ties are broken numerically. And if this is impossible, then we will mark it as such. And so we can take a moment to think about this. And we're going to maybe remember that DFS post order means you mark all your children first before you mark the parent. And so, for example, doing it on a mini tree in DFS post order, we would only mark A after having seen all of its left child and all of its right child. And so the order here would be B, then C, then A, assuming we break ties alphabetically. But the key here is that A gets visited last because it is the parent and we have to visit the children first. So knowing this, maybe we can start going in order and seeing if things look possible, right? If we visit 8 first, if it's the first thing that we mark, that must mean we've seen all of its children, right? The whole point with the post order is that you can only mark something once you have seen all of its children. And so clearly, if 8 is the first thing being marked, we must be traversing coming from this direction or coming from 4. This might not be super obvious, but we're just going to consider, imagine if we had started at 8, right? And then we could say, oh, we've marked 8 if we've seen all of its children, which would be everything here. But then those nodes would have come up first in the order, right? So therefore, we couldn't have started at 8. We must have started somewhere else in the graph, and we're traversing it this way, such that we can say, oh, look at 8 doesn't have any more children, and we're all good to go. And that's why we can mark it. So I want to emphasize, we're sort of visiting this edge. Imagine we're going from 4 to 8, such that 8 has no more children. Because if we had been starting at 8, then we would have to go from 8 to 4. And now that opens up this whole tree of children, and we wouldn't be able to mark 8. So we know that the start vertex must be somewhere here if this is possible. And then we go up and we see that the next thing in our list is 4. And so we can take a moment to think about this. And again, we recall in DFS post order, we only mark something if we have seen all of its children, right? And so we're going to imagine that we have 4 right here, and we've seen 8 already. But if we've only seen 8, have we seen all of 4's children? Whether the start was here and we were coming from this direction, or the start was somewhere here and we were coming from this direction, would all of 4's children be seen? And so we're going to recognize that if, let's say, the start vertex was somewhere in this whole subtree, or subgraph, sorry, and we had been coming from this direction, we still couldn't mark 4 because 4 has this whole branch of children that all need to be marked before 4, right? All of these nodes would have had to come before 4 in the order. Alternatively, let's say the start vertex was somewhere here, and so we had traversed in this direction. Well, then we couldn't have marked 4 until we had marked all of its children in this branch. And then 2 and 6 would have had to come before 4 in the order. And so we're realizing that this is not possible. We can't have 4 be the second thing in our DFS post order, because that would require we had seen all of 4's children branches before. And we see that based off this order, 2 and 6 come after 4, but so do 1, 5, 7, 3, which means both of these branches are getting visited afterwards, but that's not possible in our DFS post order because we can only mark 4 once we had seen all of its children, whether we're coming from this way and we consider this branch the children, or whether we're coming from this way and we consider this branch the children. Again, this goes back to that whole idea on an undirected graph. It might not be super clear what those children relationships are, and technically they're more accurately described as neighbors. But the point is that we need to visit these like sub graphs coming out from 4 before we say we've marked 4. And so this is impossible. Great. And now lastly, we want to know, suppose we have a DFS preorder of 1, 2, 3, 4, 5, 6, 7, 8 in numerical order. In the original graph, there is no vertex or start vertex that could possibly yield this order if we perform a preorder traversal. How many edges would we have to add to the graph so that this preorder traversal is possible? And so we recall in preorder traversal, we mark the parent as soon as we see it, which means we're going to be starting from 1. And now we want to see how many edges would we have to add so that we go to 2 next, and then 3 next, and 4, and so on. And so I'm going to mark edges as we go along, and we'll see how many we need to add in order to force this order to work. So we know we're starting at 1, just because like in part B, if we wanted preorder to start at 8 or have that be the first thing visited, we would start there. And same here, if we want preorder to have 1 first, we should definitely be starting at 1, so that we'll mark it. And then we need to be able to get to 2. And we're going to note 1 does not have any direct edges to 2, which means as it currently stands, we can only go to 5 and then mark that, or we could have gone to 7 and marked that. But that's not the behavior we want. So right away, we need to add an edge from 1 to 2. Great. So now we see that 1 would visit 2 before it visits 5 and 7 because we're breaking ties numerically, just like before. Okay, great. Now the next thing we would need to visit is 2. But again, 2 doesn't have a direct edge to 3, which means it would not be visited next in this DFS preorder traversal, right? Because we're going to go from 1 to 2, and then 2 will pick another edge from here because we're going to dig deeper on 2 or go deeper on 2's children / neighbors, and we would have picked 4. So we need to add this edge connecting 2 to 3, such that now when we dig deeper on 2, hit that recursive do it again button, we'd go to 3 next. So now we're at 3, and very similarly, we realize 3 doesn't have a direct edge to 4. So we're going to add that. Cool. And then we see 4 does in fact have a direct edge to 5. So we're all good here. And so we add this. And now 5 has a direct edge to 6, which means this will be visited next. Then we're going to ask ourselves, do we need to add an edge from 6 to 7? Well, what if we didn't? we're going to consider the fact that if there was no edge from 6 to 7, what would be visited next? Well, in the DFS preorder, as we're constructing it right now, we go from 1 to 2. Then we go from 2 to 3. Then we traverse this edge to 4. Then we visit 5. And then we added this node so we can go visit 6. And if we just didn't add an edge from 6 to 7, we see we're going to come back up to 5 or return to 5 and go, okay, where did I leave off? Did I like do everything? Did I visit all my children? And then 5 would go, oh, I have this edge to 7. I have to go visit 7 next. And so it would come back up to 5 and say, where did I leave off? 7. And we go ahead and mark 7 after 6. Then we go back up and we say, okay, 5, are you all done now for real? And we go, yeah, we've seen all 5 children. Let's go back up to 4. And so we move our way back up to 4 and we say, okay, where did I leave off? 4, do you have any more children? And it does. 4 has this child 8. And so we get this order 1, 2, 3, 4, 5, 6, 7, 8. And the edges that we added were the blue edges I've drawn below, connecting 1 and 2, 2 and 3, 3 and 4, and 5 and 6. And so these edges make it possible for us to traverse in the 1, 2, 3, 4, 5, 6 order. This sums up to 4 total edges. And so we realize we need at least 4 edges so that a pre-order traversal could yield this order from some start vertex, specifically 1 here. And that is the whole problem. Thank you for watching.